Okay, it's February 2nd, and we're in the backyard in Chelmsford. And this is a snowstorm just finishing up, and we're basically buried under snow right now. We got 70 inches so far this winter, but this is a good time to see if we can find Fibonacci. I think he's out in this woods someplace. I first thought maybe I could find a pine cone, but I couldn't find any. Maybe it's the wrong time of year. Then I was thinking, maybe Fibonacci is inside these leaves, these needles, these pine needles. So what I'm going to do, I'm going to take one of these pine needles off of this pine tree and see if there's Fibonacci inside it. Okay, we're back inside, and I brought in this little branch off of a pine tree. I don't know exactly what kind of a pine tree it is. And I think Fibonacci might be hiding in here. Now what I'm going to do is, I'm going to try to count these little packets of needles. Because if you look at this branch, you'll see that each needle happens at a different height. But it's also rotated by a certain number of degrees. So they almost look like they're spiraling around. Now, if I take this as the one I'm going to start with, it's the lowest one. And then I look straight up until I find one that appears to be almost directly on top of it. That would be this one right here. In other words, it's aligned. It's gone around an integral number of times. Now, what I'm wondering is, how many needles does it take to get up to that one? Now, this one right here is almost aligned, but it's still rotated a little bit more, like maybe an extra 30 degrees. That one looks very close. So that's the one I'm going to try to use. Now I'm going to try to count these needles, and you might be able to count with me, but I'm not sure if the video is that good quality. So this is the first one. 1, 2 is over there. 3 is here. 4 is back there. That's 5. 6. 7 is there. That's 8. That's almost aligned. That's 9. That's 10. That's 11. That's 12 over there. That's 13. The one that's almost perfectly aligned is 13 needles away. That's 13. That's funny because that's Fibonacci. Now, the next question is, how many times did you rotate around to get to that spot? Like, the first rotation was about here. After 1, 2, then you cross the first rotation. 3, 4, 5, second rotation. 6, 7, 8 is just at about the third rotation. 9, 10, that's the fourth rotation. 11, 12, and 13 shows up right at about the 5th rotation. That's another Fibonacci. Now, I think Fibonacci is in here. I think he's buried in the DNA of this pine tree. He's probably buried in our DNA too. Now, if we know that there were 13 needles in 5 rotations, we can find what the degree is. We could take 360 degrees times 5 rotations is the total number of degrees. And now there were 13 rotations. That's going to give us the number of angles on each rotation. I can see just by looking at it that it's about 120 degrees, but I want to know more accurately. So I'm going to go to the calculator on my computer. Now I'm going to take that and calculate it. Calculator says 360 times 5 equals, that's 1800. And divide it by 13. That comes out to 138.5. 138.5 degrees. Okay. 38.5 degrees. So, if we look at a circle, and if we look at the first, or you might call it the 0 point, that's like the first needle packet. The second needle packet comes out here. So we're at about 138 degrees, then the 38.5. Okay. The second one is rotated again. It's down here somewhere. It's twice that. It's it's actually, yeah, let's see, it's about 270 or so. It's down here somewhere. Yeah, somewhere down there. And then so on and so forth. Now, the question here is, it's if it's 138 degrees, then that means that the number of rotations, the number of needles we'll get in every rotation, per rotation, the number of needles per rotation is going to be 360 divided by this 138.5. That's good. That should be the same as this number here, 13 over 5. That's what we observed as the number of needles per rotation. That is the number of needles. And that 13 divided by 5, see what that comes out to. 13 divided by 5 equals, that's 2.6. 2.6. Now, these are Fibonacci numbers. That's like 1, 1, 2, 3, 5, 8, 13. You see, these are not adjacent Fibonaccis. There's actually a Fibonacci between them. The ratio between these two is not approximately the golden ratio, because the ratio between the 13 and the 8 is approximately the golden ratio. The ratio between 13 and 5 is going to be approximately the golden ratio squared, because the ratio of 13 to 8 is approximately the golden ratio. But then the ratio of 8 to 5 is approximately the golden ratio. So to get from 13 to 5, that's twice that you have to multiply by the golden ratio once to get down to one of the numbers. Then you have to multiply by the golden ratio again to get to the other number. But the golden ratio squared, we know that that's actually equal to the golden ratio plus 1. And we know that that's about 2.6, because the golden ratio is about 1.6. Now, if the angle between each of these needle packets is about 138 degrees 0.5, that means the way this little thing grows, the number of needles in each rotation is going to be 360 divided by this 138.5. And if I multiply that, I got to multiply 360 divided by 138.5. 138.5. That's equal to, oh, hold on, I got to do it again. I got that wrong. Got to clear it. 360 divided by 138.5 equals, no, come on, give me a break. Doing it wrong. 360 divided by 138. Oh, I was missing a decimal point. I was hitting the wrong number. Anyway, this comes out to 2.6. It's actually 2.599, but that's okay. 2.6. Now, what that means is, because because this is 138 degrees, that means whenever you count the number of needles in a certain number of rotations, and whenever you divide the number of needles by the number of rotations, you're going to come up with a number that's going to be close to 2.6. But 2.6 is very close to the golden ratio squared, which means it's going to be very close to the ratio of two Fibonacci numbers, but not adjacent Fibonacci numbers with a space in between. So that's why when I first looked to see which of these would be directly on top of it, I went up to, and it was the 13th needle that was very close to being directly on top of it. The 8th needle, which was close to actually being on top of it, that was after 3 rotations. After 3 rotations, there were 8 needles. After 5 rotations, there were 13 needles. So it's close. Now, I'm not saying that this is exactly right. See, it's not exact. The 13th needle wasn't exactly on top of it. And come on. This is nature. I can't. It looks like it's a teeny bit more. How can I measure that angle that carefully? But if I'm just counting the number of times around and the number of needles, I have to come up with an integer number for the number of times around. And you're going to come up with a number that's going to be very close to 2 Fibonacci's. If I kept going on going, the numbers get very high. They'd still be close to 2 Fibonacci numbers. One of them might be a little bit up. Maybe it's not exactly a Fibonacci. But still, that's incredibly amazing. That's almost hard to believe that would come out that way. But it does. And Frosty wasn't even here to see it because he's over on the couch sleeping. Okay.